Okay, so for our class activities for Chapter 25, Sections 1 through 3, we're going to cover concept questions 1, 2, 3, 4, and 5, and then exercises 3, 6, and 37. So again, you can turn off the video now and go just work on all of those, and then come back and find places where you need a little bit of help, where you can go one at a time, and I will pause and for you to go work on things by yourself. And so I encourage you, every time I pause, that's a note for you to stop the video and think about the next steps to help you try and make as many connections on your own as you can. And so if you feel like you're comfortable with the problem, you can just fast forward beyond it, and I'll try and make that as easy as possible to do. Okay, so we're going to start with concept question 1 right here. So stop the video, go work on that, and come back. Alright, so concept question 1, it's about the potential energy of a charge Q1 related to Q, and we have this Q1 is some distance away from a big Q. So here's one charge, here's another charge, and they're a distance r apart. Okay. And then the question is, well, what happens if you have another charge near the big Q, Q2, and its size of charge is 1/3 the size of Q1, and it's twice as far away? What is the ratio of the potential energy? So what is the main idea here? What's the main idea? Okay, so potential energy of 2-point charges is the main idea. And so we find the potential energy, okay, between these two charges is going to be equal to K Q1 times big Q over R. Okay. Now I want to point out here that this is awfully similar to the force between two charges. There's one slight difference, and that is it's over r to the first power instead of r to the second power. So otherwise it's just the same, and you have to be very careful to make sure you remember the difference. And there's a conceptual difference too, that this is not a vector. This is just a number. It can be plus or minus, it can be positive or negative, but it doesn't have any direction associated with it, and that becomes an important thing. This is just potential energy. It's like gravitational potential energy. It's the the energy that's stored ready to do work. And so you can think about that these two particles, if we assume that they're both positively charges, they're going to shoot away from each other. They can speed up. And so this potential energy can be turned into kinetic energy. But it's just some form of energy that's stored in the interaction between these two. Okay? So with that in mind, here's the main idea. This is the potential energy between 2-point charges. And the question is, well, what happens if we change it so that a new charge has 1/3 the size charge as Q1, and it's twice as far away? So what do you do? Okay, so hopefully you said, well, that would go to K and Q1 over 3. Big Q doesn't change. And then 2R. Alright? And if you factor those out, that's going to give you 1/3 times a 1/2. We have a third in the denominator, a 2 in the denominator. So it's going to give us a 1/6 K Q1 big Q over R, which is 1/6 U. I'll call this U1. Just for U1. So this is all about proportionality. How are these proportions? Okay, now in part B we do something similar. Okay, part B we say that now the instead of two charges, we have a charge inside a capacitor. So what's the main idea there? The potential energy of a charge inside a capacitor is what? Okay, so the potential energy of a charge inside a capacitor is the Q, the size of the charge, so Q, we'll call it Q1 in this case, times the electric field inside the capacitor, times the distance from the negative plate. Now, potential energies, if you remember gravitational potential energies, the zero of potential is your choice. For gravitational, I could choose my desktop to be 0, okay? Vertical is pointed up at you, okay? And so I could choose that to be 0, and so if I raise a ball towards you by 1 meter, I would give it, that amount of potential energy. But I could also measure it from the floor. And I happen to be sitting in a treehouse right now, about 30 feet up in the air, so I can measure it from the ground outside, the dirt outside. So your reference is ambiguous, and so this potential here is also ambiguous. But it doesn't really matter, because all we really care about is changes in potential. What happens when I move a charge from this position to a new position? And it's that change of potential that is not ambiguous. It is unambiguous. The difference in potential energy doesn't change based on your reference. So that's just a note to remember, that potential energies are based on some reference point, but changes in potential energies are not. So we can choose S to be the distance from the negative plate and choose that to be our 0. That's kind of a standard to choose that. And so with that being our choice here, then what we're saying is now we have the same changes. Our new charge is a third the size of Q1, and it's twice as far away. And so hold on to that arrow there. So now we get Q1 divided by 3 times E. The capacitor never changed. We didn't do anything to the capacitor, okay, but we do move it a double the distance, so 2S1, and so here we get 2/3 U1, okay, because the 2 would come out 3 and we'd be left with the Q1ES. So again, it's all about knowing what this equation describes what. This is specific to 2-point charges, this is specific to a charge inside a capacitor, okay, and how are they proportional. Okay, very good. Let's move on to number 2. Go take a look at number 2 and try and solve it. Okay, so number 2 has that graph. Okay, now that graph is about like this. I'm going to draw a 20 and a 10, a 1 and a 2, and the graph looks something like that. And these units here in femtometers, or 10 to the negative 15 meters, and the units here are in 10 to the negative 12 joules. Okay, so I'll leave you again, reference your picture. So what does this tell us? This is potential energy as a function of separation distance between two charges. One of them happens to be a proton, and one of them is a lead nucleus, which has a charge of plus 82 E. E being the charge, the fundamental charge, same charge as a proton or electron. Okay, so these two charges should repel each other, which means if you get them close to each other, then they're going to want to go apart. So the closer they get, the more potential energy they have. They have the more potential to speed up. Okay, so this makes sense. The closer they get, the more potential energy they get. And the further they are away, the less potential they have. In fact, if you go far, far away, it's pretty much 0. Okay, never truly 0, but pretty much 0. Okay. All right, so understanding this graph and thinking about this as potential energy as a function of separation distance, see if that helps to understand how to solve this problem. Go ahead and pause now. Okay, so in the first question, it's trying to say how much initial kinetic energy does the proton need to reach a turning point 10 femtometers from the nucleus if it's starting far, far away. Okay, now it's been a while in this class since we talked about energy, but this is just a conservation of energy problem. And so let me encourage you to try doing this. So this is part A. We have initial kinetic energy plus initial potential energy. And assuming there are no works done from outside the system, which this is fine, we're using the two charges as our system, and that should equal our final kinetic energy plus our final potential energy. That's conservation of energy right there. In fact, conservation of mechanical energy, because we're assuming no thermal energy or any external work done. Okay, so this is a review. This is definitely a review from a while ago. But now think about what that means. Our potential energy is the potential energy of a point charge. Well, we've already worked with that one. So we know what the potential energy of a point charge is. And in fact, we can read it off this graph for different distances. Okay? Now the question is, do we know some of these values, some of these other values? Okay, well, first of all, think about what the problem says regarding our initial potential energy. Remember, it says that they are far away, very far away. What does that mean about potential energy? Think about this graph. We go very far away. Okay, hopefully you got that. This potential energy is 0. Okay, as this gets far away, this gets so close to 0 that it's effectively 0. Far away for potential energies is code word for 0. When two things are super far away, the energy of their interaction is pretty darn small. Okay, do we know, are any of these other quantities 0? Okay, well, maybe let's back up. What are we even looking for? We're trying to find how much initial kinetic energy it has to have in order to reach 10 femtometers away. Okay, that means this is what we're looking for. How much kinetic energy do we have to start and in order to get 10 femtometers away? But what does that get 10 femtometers away? What does it mean? Okay. What does that mean about K1? What is your final kinetic energy if you reach a turning point at 10 femtometers? That should be 0. So in this case, our final kinetic energy is 0 because we reached a turning point and stopped. Okay, well that makes this easy. That means our initial kinetic energy is simply equal to our final potential energy. We have all kinetic to start, and we lose it all in increasing the potential energy. It's like rolling a ball up a hill. I give it a big push, lots of kinetic energy, rolls and stops. But now it's got the potential to do something, roll back down. Okay? And so that's what we're seeing here. So now I just have to read this off the graph. This one state, my final state, was at 10 femtometers, so that's right up there, which is a value of 2 times 10 to the negative 12. Remember, these are in units of 10 to the negative 12 joules. So my initial kinetic energy is 10 to the negative 12 joules, just by conservation of energy. Okay, well with that in mind, take a look at B. Go try and solve B. Alright, now B just may be a little bit confusing on the wording. So let's read it together. How much kinetic energy does the proton of part A have when it is 20 femtometers from the nucleus and moving towards it before it stops? Okay, so what's that saying, just to clarify, is in this first case, we had it far, far away, it came towards and came and stopped right there at 10 femtometers. What part B is asking, saying, on its way in, how much kinetic energy does it have right here at 20 femtometers? Okay, that's what it's asking for. Alright, so see if that helps you to solve this problem. Okay, so how is this different than the previous problem? Well, the main idea is it's still conservation of energy, and so I just need to have a different state. I'm going to call my initial state, okay, I'm going to call my initial state to be right here, okay. So I'm going to have that K0 plus U0. But now just remember that's state 0 in this case for part B, and this is state 1 for part B. Now that's different than the states I chose up here for my indices, so you have to make sure you keep things straight. Okay, but that's going to equal K1 plus U1. So my initial state for part B is here. My final state for part B is here. Alright, so with that in mind, can you find this unknown kinetic energy? How much energy does it have right here? Okay, K1 is the same K1 we had up here. It still stopped up there, so that's still 0. It still stopped. U1 is still this value, so I know that one. The question is, well, what is U0? It's not 0 this time, because it's not far, far away. But I can read it off the graph. And so I can rewrite this now and say K0 is equal to U1 minus U0. And I'm going to have U1 is 2 minus 1. This is going to give me 1 times 10, negative 12 joules. Okay. So this is really powerful. Conservation of energy is a super fundamental law, super fundamental rule, and it comes into play whenever there is an interaction between objects. Okay, now we're ready for number 3. Go ahead and look at exercise 3. Okay, now that you're back, here's our positive charge. Here's initial position, final position. Here's our electron. And it's going from the initial to final position. Okay. And part A says, does the electric potential energy increase, decrease, or stay the same as this electron moves from the initial to final position? Okay, well, what's the main idea here? Okay, the potential energy between 2 point charges, these are 2 point charges, the potential energy between 2 point charges is equal to this constant times the size of the charges. I'm just going to put Q1 and Q2 here. Okay, we can call this 1 and this 2. And divided by the distance between them. Alright? So, does the potential energy increase, decrease, or stay the same? Okay, now if you looked at this and said, well, in the initial case, R is small, which makes U big. In the final case, R is big, which makes U small. You say, oh, well, the potential energy got smaller. And that is correct if we're asking for magnitude. What's the magnitude of this? But we need to be careful in this particular situation. That's a negative charge and that's a positive charge. So overall, we have a negative in this. So our potential is actually a negative times the magnitude of this. So if our magnitude got smaller, okay, but the values are actually negative, then did our potential get more negative or less negative? It got less negative, which means it got bigger. Okay, less negative is bigger. So if I draw a potential energy scale here, here's my potential energy, and I was bigger down here, and then I got to here, okay, this number is a number closer to 0, but that's above this number. This is more negative than this one. So you just have to be careful. Potential energies can be negative, and they will be negative if your charges are opposite signs, in the case of two charges. Okay, so it becomes less negative, or in other words, it gets bigger. So delta U is a positive number. All right. Now part B asks a question about the speed. Is the object's speed bigger, less than, or equal to at its initial speed? So think about that one. Alright, so hopefully you're able to go back to some of these ideas up here of conservation of energy. Okay, so if I gain potential energy, then what happens to my kinetic energy? as it should get smaller. You can rewrite conservation of energy, mechanical energy look like this, is delta K equals a negative delta U. Okay. In other words, if I gain, or if I gain potential energy, I lose kinetic energy and vice versa. So in this case, the particle would slow down. Now we can check that. We can check that without even thinking about energy. We can think about forces. Okay, what is the force between these two charges? The force, is it attractive or repulsive? And it is attractive. They're opposite charges, and opposite charges attract, which means this negative charge is attracted to this positive charge. So if it's moving like that, that means it's moving against this pole, okay, which means it should slow down. And that's indeed what we found here. Our kinetic energy is decreasing because our potential energy is increasing. Okay, very good. Now let's move on to number 4. Okay, so number 4, you see a capacitor, the negative top plate, positive bottom plate, and you have a positive charge, okay, in fact, a proton. And in one case, the proton is launched from this location 1, and it ends up going straight there, straight towards the negative plate. Okay, so it's launched with some speed, and it gets to point 2, following that path. A second proton is launched with the same speed, but this way. And it curves because of that attractive force towards that negative plate. It curves that way. The question is, what is the how is delta U between 1 and 2? How is it in size related to delta U between 1 and 3? In other words, does the change of potential energy in going from 1 to 2 differ, or is it the same than the change of potential energy in going from 1 to 3? So hopefully you recognize that sideways motion has no bearing on the potential energy of a charge in a capacitor. What is the main idea? Well, the potential energy of a particle inside a capacitor, we've already done. Okay, we've already done. It is equal to the charge times the electric field times the distance. Now that S, it has meaning, so this is something where we need to know what our variables mean. S is the distance across the plates, okay, starting from the negative charge. It's simply the distance, the perpendicular distance across the capacitor. So if I move along the capacitor, along the gap, it makes no difference. So I could shift from here to here, and there's no potential energy difference. Likewise, I can go from here to here, and there's no potential energy difference. Which means if I have some potential energy here, and I get to here, I get some change, because I had some change in S. But my change in S is the same amount, because S is only this much. It's only the distance across the plate. So that means that delta U 1 to 2 is equal to delta U 1 to 3. There's no difference between them. Okay. Now, if we try to answer that question, well, sorry, let's take a step back. Let's do part B. Okay. Part B is, how's the speed at 2 relative to the speed at 3? Is it bigger, smaller, or the same value? Knowing that they start with the same speed, it's just one shot straight towards the negative plate, the other one shot sideways. How does the speed change? Okay, so thought about that. If we think back to this right here, that helps us to see that. Delta U12 equal delta U13. Okay? So the change in potential energy is the same whether I go from here to here or go from here to here. Which means delta K should be the same for each of them. Now that might bug you. You might say, well, no, it's moving this way faster, and this when it moves shot this way, it has no velocity this way. So this one maybe should be slower. But what we're forgetting is that this kinetic energy is the total kinetic energy. It's not. It doesn't have components. This is a number. It doesn't have components or direction. And so the total velocity would have something like that. It indeed would have a smaller component directly across, but it has also a component across, along the gap. And so that speed is going to be the net result of the vector component of those two, and it will be the same size as the speed here. Okay? And we can find that very quickly. We could solve that with forces and kinematics, but that'd be a pain in the rear. But energy makes it so much easier. We could say that delta K 1, 2 is equal to delta K 1, 3, simply because of our conservation of energy. That's it. That's an important point. It's an important concept to understand. What does potential energy rely on? What does kinetic energy rely on? And to not get those confused with the vectors of forces and velocities. Kinetic energy is just size. How big is the speed? Not necessarily what its directions are. Okay, let's move on now to number 5. This is a different problem. Okay, this is a different problem. Go ahead and look at number 5. Okay, so what we have is we have a dipole in a uniform electric field. And the question is, rank the potential energy for all these dipoles. And they have different orientations. What's the main idea? Here's my electric field pointing this way everywhere in all space. And I've got a variety of configurations. I've got plus and minus, I've got plus and minus, I've got plus and minus, minus plus, plus, minus, and plus, minus. I've got them all like that. What's the main idea here? Let's shift this over a bit. Okay, what's the main idea? Okay. If you think about forces alone on this, this actually makes it kind of easy. This one's a little bit easier to think about with forces. If the electric field is pointing to the right, what do positive charges want to do in an electric field? They want to go in that direction. Okay. And a negative charge wants to go in the opposite direction. So one thing about this, even though there's no net force on dipoles in an electric field, they want to align with the electric field. Okay. So it's easy to see on this one, this negative charge feels a pole that way, and this positive charge feels a pole that way. And you can see that orientation is going to make it want to align like that until the pole is opposite each other. Now it can't do anything more. Okay? And you can do that with all of these and see that they're all going to want to align like this one. Now if those are aligned and it wants to align, that's like a stable state, which means it has the lowest amount of potential energy. Remember, like a ball on top of a hill has a lot of potential energy. Even if it's at the very peak of a hill, if we have this ball on a hill right there, if I give it one bump, it will roll down the hill. So it has a lot of potential energy. But if it reaches a valley and sits here, it's at a stable state. I can give a bump that keeps wanting to come down to here. So this is a lower potential energy. So if you think about all these dipoles, they all want to look like that one. So that is like our valley. It's got the lowest potential energy. This one right here is like our ball on top of the hill. It's got our highest potential energy because it's opposite what it wants to be. Now this one, it's intriguing. In order for that to flip, it needs to be kicked because it's like a stable point. Well, it's an unstable, but it's in equilibrium. In order for that to move, it has to give a slight kick either direction. Same thing here. The force on this one is this way, and the force on this one is to the left. Okay? But they're exact opposite each other. But if you slightly move this at some angle, suddenly it can flip around. Now these other ones are simpler. This one would want to flip that way, this one would want to flip this way, but it doesn't matter which direction they flip. And so that's like being on the hill over here or being on the hill over here. It doesn't matter. Okay. So with that in mind, the main idea is that these want to align with the electric fields, with the positive in the direction of the electric field. So now how do we rank these? Okay, so the answer should be, with A, B, C, D, E, F, should be UA has the greatest, and then UC is the next grade. It's most misaligned next to this one. Okay. Then UE and UF have the same, because they're both perpendicular to the field. It doesn't matter if it flips left or clockwise or counterclockwise. So those are both greater than UB, and that is greater than UD. D is the lowest potential. Okay. Very good. So those are our concept questions. Now we're going to move on to the exercises. So go ahead, take a look at exercise 3. Okay, exercise 3. Okay, what do we have here? We've got a proton released from rest at the positive plate of a parallel plate capacitor. It crosses the capacitor and reaches a negative plate with a speed of 50,000 meters per second. What's its final, or what would be the final speed of an electron that was released from rest at the negative plate? Okay, so this is a conservation of energy problem again. All right, so in the first case, we have, we'll call this the positive, this is negative, a positive plate, or it's released from rest at the positive plate, so this is a positive charge. It flies across here and gets to here. Okay, and we know the velocity here. All right, now I'm not going to do kinematics here because we don't need to do that yet, or we don't need to do that. We can use energy to solve this. And then the question is saying, well, what if I release a negative one here and it ends up over here? Okay, it's going to end up over there. Okay, so the thing is that these have the same size charge, just one's opposite the other, but that also just means one's going to move the other way versus one's going to move left versus right. And so when we think about the potential energy change, okay, we're going to have the same potential energy, because the potential energy of a particle, of a charged particle in a capacitor is just Q ES. And if they go the whole distance here, then delta U is just Q E D, if we call that D. Okay, so S is the position relative to the negative plate, and D is the total distance across. So delta U would be the difference in their positions, which in this case is from 0 to D, or from D to 0. But given that the charge, so the sign of a D changes because they go different directions, but the sign of Q also changes, so it doesn't matter. We recognize that the change in potential energy is the same. As the positive speeds up, it's gaining kinetic, losing potential, and as the negative speeds up, it's gaining kinetic, losing potential. So that's the first thing to think about, is their potential energy changes are the same. Okay, well with that, go ahead and think through if you can take some next steps on your own. Okay, so we're trying to find the velocity of the negative, or the electron, if we know the velocity of the proton. Okay, so let's just look at the proton first. So let me put that little plus there. Okay, so I know that my change in potential, let me put plus for my proton, is equal in magnitude, or opposite the change in kinetic energy of that proton, which it's speeding up, which means that's going to be equal to just K final of the proton. All right. And that's the negative sign just means I'm losing potential and I'm gaining kinetic. So I got this is a negative number canceling that negative number. So I really only need to worry about the positives. Okay, well, what's the change in potential? Well, I've got it right here. So I can come down here and just say that K final, again, this is magnitude, so I'm going to worry about magnitudes only. And so I'm going to K final to the plus is going to be Q plus E D. Alright? And that's just E, E, D. Again, little e stands for the charge of an electron or a charge of a proton. They're just opposite in sign, but we've noted that we're just working with magnitudes here. Okay, well, with that being said, that means my velocity, this equals a 1/2 m plus v plus squared, 1/2 mv squared for the proton, equals E, E, D. Okay. All right. Now, what is it going to be for the electron? Think about that. Hopefully, you recognize it's the same result. 1/2 m of the negative charge, velocity of that negative charge, but they have the same size charge. It's the same capacitor. They've gone the same distance. They've both sped up. So these are just magnitudes here. And we don't know the electric field. We're not given enough information of the capacitor itself. We don't know what the capacitor is. And so how do we find this velocity just knowing this velocity? Well, you can do a ratio here. What if you divide both sides? If I divide both sides, those cancel out. That cancels out. That just equals 1. And so I have m plus v plus squared over m minus v minus squared equals 1. Or in other words, solving for v minus, that's going to equal v plus times the square root of the mass of the proton over the mass of the electron. Okay. So this is great where our math helped us to very simply see how the velocities are related. Since everything else is the same, they're only different by their masses. Okay. And so that helped us to find that. The final answer would end up being v minus equals 2.14 times 10 to the 6 meters per second. Okay, so again, most important point is we had conservation of energy. Next most important point, we recognize that they're both having the same change in potential energy. Okay? And then we use those two ideas together to cancel out things we didn't know to be able to solve for our final value. Okay, go ahead now. We're going to do problem 6. Problem 6. Okay, so what is the potential energy of a system of charges? What's the main idea here? We have these 3 charges, and this is a positive one, a negative one, a negative one. This is negative 2q, and plus 1q. And they're all a distance, I'll call it d apart, where q is 1 nanocoulomb and d is 3 centimeters. How do you find the potential energy of a system of charges? What's the main idea? Okay. If you remember that the potential energy is an energy of interaction. So you have to have 2 things to create a potential energy. So for gravity, it's the earth and a ball, or whatever it is. Here, it's every pair of charges. So this charge down here interacts with that one, and it separately interacts with that one. This charge here interacts with this one, and it separately interacts with that one. And you could say that by every pair. So every line between charges is an interaction. So the potential energy is simply the potential energy of a pair of point charges for every interaction. So go ahead and see if that helps you solve this. Okay, now that you've thought about that, we can write this out as U of the system is equal to potential energy between each pair. So I'm going to give these names 1, 2, and 3. Okay? So it would be the potential energy between 1 and 2, plus potential energy between 1 and 3, and plus potential energy between 2 and 3. Okay? Those are the three different possible interactions. Okay? And so, what are they? They're all point charges. So between 1 and 2, that's K, Q, and negative 2Q over D, plus 1 and 3, it's the same thing, so I just have two of them. I'll go ahead and write it separately. K, Q, negative 2Q over D. The last one is between these two, which is plus K, negative 2Q, negative 2Q over D. And now you can see why I was being wise in writing my charges and distances in terms of this common variable. Because I can pull that out. I have a K. Each term has Q times Q, so there's a Q squared. Each term has a D. So I can pull that out. And what am I left with? Well, it's times a negative 2 on that one, plus a negative 2 on that one, plus a positive 4, because negative 2 times negative 2 is positive 4. And that gives me 0. Okay. So what's the main idea? Potential energy is an energy of interaction. For systems of charges, you just add up the potential energy of each unique interaction. Alright, finally, I'm going to move to number 37, problem 37. Okay, so problem 37. Now this one, the setup, the conceptual idea, this is decently simple, but it has a little bit more math to be able to solve it. But I wanted to use this as a good exercise for an in-class activity, not necessarily one where I'd use in a quiz or something, because it's got a little bit more math than concepts. Okay, but it's not any math we haven't seen before. Okay, so what's the main idea? We have these two charges, charge 1 and charge 2, and they're separated by some distance d. Okay, we know d. D is 0.02 meters. Okay, we know that the sum of the charges, Q1 plus Q2, is 30 nanocoulombs. Okay, and then we know that the potential energy between them is a negative 180 millijoules or microjoules. What are the values of Q1 and Q2? Okay, so how do you do this? This would be a good example of one where we really should write down our full process. So what are some things we know? Okay, so we know D is 2 centimeters or 0.02 meters. Okay, we know that. We know that Q1 plus Q2 is equal to big Q. I'm just going to call it big Q. And that's equal to 30 nanocoulombs, or 30 times 10 to the negative 9 coulombs. And lastly, we know that U12, the potential energy between those two, is equal to a negative 180 microjoules, or negative 180 times 10 to the negative 6 joules. Okay, and what are we trying to find? We're trying to find Q1 and Q2 separately. What are their separate values? Okay, so with that setup, what would you do next? What main ideas and main concepts would you start with? Alright, hopefully the main concept we have is a definition of the potential energy between 2 point charges. Okay, so if I start over here, we have U12 is going to be K, Q1, Q2 over the distance between them, which in this case is D. Alright, I have this value, I have this value, and that's a constant. And so I can find this. So I have Q1 times Q2 equals some number I could find. Right? Then I also have this over here, that Q1 plus Q2 equals another number that I have. And so here we have two equations and two unknowns. So go ahead and see if you can solve that. And I'll give you a little bit of a hint. It's going to be quadratic, so you have to choose quadratic formula. Okay, so let's see how we can get this looking like the quadratic formula. So, you can go in multiple directions. How do you want to do it? I'm going to go ahead and first clean this up. So I'm going to have this be du, and I'm just going to leave off the 1, 2 for now, divided by k. Now, I see a lot of integrals in my work, and so this jumps out at me as a derivative of u, but this is not. D is a distance, and u is a potential energy. So this is not a small bit of u, as we've kind of seen in the recent past. So remember, these are two separate variables. Okay, so that's du over k equals q1, q2. Well, what if I come over here, and let's go ahead and replace q2 with q minus q1. So q2 equals q minus q1. Sorry, I got a little cramped there. Okay, so big Q minus Q1. So I have distance times potential energy over K equals Q1 times big Q minus Q1. Okay. Alright, now see if you can get that in quadratic form. Okay, what would be some next steps? Let's go and factor this out. We have Q times Q1, and then we have negative Q1 squared. Now the form I want is ax squared plus bx plus c equals 0. In this case, q1 is our x. I need to find those. I need to get in that form. So I'm going to go ahead and add q1 squared to the other side. So I have q1 squared. Subtract this to the other side. Subtract big Q times q1. And this is already on the other side. Plus d times u divided by k. And I'm left with nothing on the other side. So this is 1 times q1, a equals 1, negative q, so I have b equals negative q times q1, and then c equals du over k. And so I have it in quadratic form, and I see what my coefficients are. Okay, now carefully plugging that in, recognizing that u is a negative 180, and putting in correct units. Again, that's 180 times 10 to the negative 6. This is 30 times 10 to the negative 9. Plugging those all in, you will end up with Q1 equaling 40 or negative 10. It can be either. And so usually when you have a quadratic formula, you always get two answers, a plus or a minus, and you have to say, well, which one's reasonable? Well, in this case, Q1 could be 40 or negative 10. Because Q2 could be the other way. Okay. So if Q1 is 40 and Q2 is negative 10, well, Q1 plus Q2 is 30, like it ought to. And they're opposite sign like they should, because the only way to get a negative potential energy is with opposite sign charges. Or if Q1 was negative 10, well, then Q2 would be 40. It still works. It doesn't matter the position of these two. That's why Q1 could be either. It doesn't matter which one goes where. So we can just choose that one if we'd like to. Okay, and those would be in nanocoulombs. All right, so that is the end of this lecture.